So this is our unit 5. This is momentum. Again, it has two big ideas: impulse momentum theorem. So what is impulse? What is momentum? So that we can get to the impulse momentum theorem, and then conservation of momentum. Those are the two big topics inside this unit. And like I said, it directly relates to what we just spent the last 6 so weeks on Newton's 3 laws of motion. Now we're going to do this, the egg drop, right? And so we have 2 weeks to do this. So you have some time to think about what you want to do and how you want to do it. We can't do this very quantitatively, meaning because none of you guys are going to be here. So none of you are going to have the equipment to use to figure out like how much force. You're all going to be dropping it from different locations and different heights. Normally what we do is we all drop it right outside my room. There's a stairwell. We drop it straight down. It hits the tile floor. Underneath the tile is concrete. So it's a very rigid, material. There's not a lot of give to the tile in the concrete. And so when it hits, it can hit really hard and exert a pretty good force. So you really have to, think about how to protect your egg in terms of force and time and momentum. Now, since you're going to be doing this at home, I have a couple ideas, and I haven't typed it up because I wasn't really sure how this was going to look virtually, but I want you guys to do this because it's one of the things that students every year look forward to and find fun to do in school. But yeah, I think you can still have a good time with it doing it at home. But it's going to be more of a qualitative lab than it is a quantitative lab. And so you want to drop a raw egg inside your container from a certain height. Ideally, it's going to be the same, at least if you're on the first floor, at least from the second floor down at a minimum. But I was thinking of trying to make it so that if you drop it from a higher height, that you get more points than you would at a lower height, to try to separate really good. Since we can't do everybody from the same height at the same time and see, how much force there is. In theory, when we did this lab, we would assume that the velocity of every container is the same, even though we have no way to know how much effect air resistance has. So that's obviously something that's going to slow down your container as it falls. And so taking advantage of air resistance is a good thing. And we would be calculating the theoretical velocity it has upon impact and its maximum amount of momentum. But in reality, because of air resistance, it would have much less than that. So even the calculations that we do here at school are flawed heavily because of that. And so the idea is you build your container so that when you drop it, I knew these were animated. You drop it so that it will fall, and not when you open it up, the egg's still good. But the other part to this is usually what we do is we make a 1 meter by 1 meter box. I tape it out on the tile and on the floor. And then when you drop it, you want it to hit there and stay there, right? So that your container absorbs that impact upon hitting the ground. It doesn't just ricochet way out and land 20 feet away, right? So we're looking for it to do two things. One is hit and land and stay in that little area, but also once we open it up, protect your raw egg. So you want to look at impact absorbing materials. And then after we talk about this impulse momentum theorem, the two things that we can control, same as engineers when you're in a car crash, right? Designing the car to control, minimizing the force. To do that, what can they do? So you want to have those same thought processes. And that's kind of where we take tomorrow's activity normally, and think about, getting you to think about, well, okay, this is what happened here. So maybe I need to look for these types of materials because these eggs are obviously very fragile. So start thinking about that. We're not the only high school in America that does this. So there's lots of people that have already done it, to get some ideas as well. These are the rules. It's a large. You don't have to use extra large or medium, just a large. You could use a bigger one if you want, but I don't know if bigger one is any stronger or weaker. But obviously uncooked, unfrozen, right? Original, almost right out of the chicken form. You can't coat it in anything or tape it, right? You got to be able to put it in and take it out, put it in and take it out. And so I envision you guys, when you do this, is filming using, so you're filming yourselves, and then maybe that class that we do this, I can show everybody's videos so you guys can all see each other go. Whether, you're a really good teachers, show you guys how to use, I can't think of the name, Flipgrid and those programs that we never use, but maybe using one of those types of programs. And then you guys send me the videos, and then I could show them through here so everybody can see everybody's success, hopefully. But again, you can't code it. It's got to be able to go into the container, and then you got to be able to open it up easily so you can say, hey, it's not broken, put it back in. Normally we get 3 drops, so you get 3 tries, but obviously you want it to be successful the very first try. If it breaks the first time, then you lose some points, but you get a second try, then you lose more points, you get a third try, kind of like that. And so I kind of made a rubric as a part of the competition. But you can't use, well, you obviously shouldn't use glass because glass is going to shatter. That would be silly. Metal, no. You can't use a parachute. You can't use gas like helium, or try to make some kind of hot air balloon that slowly brings it down. You can't use like a drone to drop it for you, right? Obviously those would be great ideas, but no. But that's kind of the idea. We'll talk more about this each class, but I wanted you to think about it. This is the lab sheet I normally give you guys. And so you see the procedure here, the rules that I just kind of showed you. We try to drop it. It's I say 8 meters, but it's actually 6 meters, I think, if I remember right over here. We want it to be in a 1 meter square area on a hard surface, so a concrete type surface. But if it's in your house, obviously it's probably going to be a tile or a wood, I would assume. You can't drop it on a carpet. Because that would be softer, and we want it to land on something hard. And then we have these penalty points and stuff, but we're probably going to have to change this based on what you guys are doing at home, and come up with a little, maybe the same penalty points, but then there's bonus points from dropping it, like if it's successful from your first floor, but then you drop it from a second floor or a third floor, if that's possible. But this is what we've done in the past. So start thinking about that, how you want to build it. And then, think about the physics involved. Any questions on that? Okay. So let's start out with momentum, right? And so if you're into sports, as I am, you watch a lot of sports, and they talk, even announcers talk about, I should get rid of Redskins now. Didn't even think about that. The, teams having momentum, meaning whether or not they've started to win a bunch of games, and now they'll use the idea of momentum. So, or if during the game, maybe a team's losing, all of a sudden they score a goal, then now, like, you see an energy involved in their play, and they say, well, they've got a lot of momentum right now, right? And so it's a term that we use a lot in sports outside of the physics realm. But it's the idea of something's really changing. There's a buildup of play, right? Something's on the move. It's going to be hard to stop. But in physics, it deals with this idea of quantity of motion. And so it has something to do with, right? So we're trying to quantify the motion of an object. So momentum is this idea of mass and motion, right? Because we're trying to quantify the motion of an object. Objects have mass. So if it's moving, right, we've got mass in motion. And if it's moving, that means it has a velocity, right? And so we're looking at the momentum of an object depending upon how much stuff, right, that's the mass, and how fast is that stuff moving. And so the two variables that we've dealt with, mass and velocity, right? Whereas in Newton's laws, we were looking at with Newton's second law, mass and acceleration. In the momentum unit, it's a little which is the difference, is we're looking at not the acceleration, but the mass and how fast it's moving, its velocity. Right? It helps us understand collisions, which I've talked a lot about with the egg lab and car crashes and things like that. But so the symbols for this, right? So you look at this, it's a really basic equation, right? Momentum equals mass times velocity, right? That's easy. That's that on your formula sheet that I showed you guys earlier. It's m times v. But now you look at this, so we know mass is m, we know velocity is v. So you look at momentum and you'd be like, all right, well, what symbol are we going to use for momentum? Somebody decided that P would be the appropriate symbol for that. I have no idea. Again, I don't know where that comes from. Is that a Greek, a Latin thing that they used something that looked like, or the M in those languages looks like a P, and so then when it translated to English, we're like, well, it looks like a P, so we'll use a P. I haven't really looked at that. I don't know those languages, the written languages well enough. But I will tell you that P is also used for power and pressure. So it's not like we're not already using the P. And it wouldn't make a lot of sense to say capital M equals little m times V, right? That would probably not help people understand the equation better. So I'm not really sure why P became the symbol for momentum. When we look at this, since we know velocity is a vector and we know mass is a scalar, when you multiply a scalar times a vector, remember a vector has something as magnitude and direction. Well, momentum is therefore a vector because the velocity is a vector. So the direction of an object's momentum is based on the direction of the object's velocity, right? Because mass doesn't have direction. And so the other thing is the unit. We know we have to have mass in kilograms, and we know that velocity is a meter per second. So you have a kilogram times a meter divided by a second. Now, if you remember, a kilogram times a meter per second squared is a Newton, right? But it's a second squared. This is a second squared. So this is the unit. Like they don't have a special unit. It is what you see. A kilogram times a meter per second. Kilogram, meter per second. That's a unit of momentum. But it is a vector quantity. That's what this little arrow above the V and the P mean, to tell you that you have to include direction with momentum just like you do velocity. Right? So it's a really easy equation. If an object's moving, you have momentum. Right? How much momentum you have depends upon is it a really big mass, or is it a really big velocity, or is it big for both? Right? And so it can be a combination. So you look at this ship, right? It's huge. It's got all these cargo things that, containers, very massive. I'm sure it weighs tons and tons of pounds, but it's not moving very fast. But there was one of these that just crashed like a week or two ago, right? Because they're so massive that they need a really long time to stop, or they need a humongously big force because they have so much momentum, even though they're not going very fast, right? Because they have such a big mass. Think about when we talked about Newton's first law, one of the questions I think was on your homework had to do with a moose, right? And so if you go up to Maine and the northern states, they have moose. They're massive animals, right? Very, very heavy, very fast, like you can't outrun a moose. Same as a bear, right? If you go hiking out in Shenandoah and you come across a bear, very massive animal, a lot of, weigh hundreds of pounds, much more than we do. And both of those animals can outrun a human. A bear can outrun us, and a moose can outrun us. So we can't then say, all right, I'm going to outrun you, because that's not going to happen. But they have so much mass that if we use that against them by zigzagging, right, making cuts, they can't cut. The saying in sports is cut on a dime. Like you plant your foot and you cut the other direction really quickly. They can't do that because they have so much mass, right? And especially with a moose with a very high center of gravity, because it has very long legs, it's going to tumble forward before it's going to be able to make a really quick cut like you do, right? And so we use that mass against them. Well, the same thing here with this mass, which it would be immense. Even if it's moving really slow, it's going to take a lot of force to slow it down. And it probably takes a very long time to slow it down. And so it has a lot of momentum. The other thing that could this was a really cool video that got taken down years ago. They did a high speed frame of a bullet going through some crayons. And so you see the picture, but right, so the bullet really, really tiny, very small mass, but a very high velocity, that has a lot of momentum also, right? So if you watch TV shows that involve shooting guns or cannons or things like that, if you shoot a rifle, you know that it recoils, right? There's that Newton's third law, but we'll look at that in terms of conservation of momentum next week, right? But these things have a very high velocity. They have a lot of momentum because they move so fast. So it's the combination of the two. And so you can have a really small mass, but run really fast, and you have a lot of momentum, or you can have a very big mass and you don't run very fast at all and still have a lot of momentum, right? So the two factors are mass and velocity, right? And so I've talked a lot about this as well. Object that has momentum, right? It's hard to stop the object with a lot of momentum, and you need a big force to do that, right? We need an unbalancing force to do that, and that's Newton's second law, right? And so, but everything takes time. So when you're applying this force to stop something with a lot of mass, which means it's moving and it has a lot of momentum, right? The time period and the amount of force are a give and take. If you can apply a bigger force, then you probably can apply it for a shorter period of time to stop the object. If you can't apply a big force, well, then you're going to have to apply that force for a longer period of time, right, to stop the object. We're staying away from the idea of acceleration, right? Because obviously force equals mass times acceleration, and acceleration equals a velocity over time. So there's the factor of force and time in there with velocity, but we're trying to stay away from the idea of talking about acceleration, which we could easily look at these same problems, the same idea about acceleration, right? So an object with more momentum, it's going to be harder to stop because it's either got a bigger mass or a bigger velocity or both. We need a bigger force, or we need to apply that force for a longer period of time. And so we have, again, the mass and velocity aspect, and then we have the force and time aspect. And then there's this idea of change in momentum. So while we are concerned about momentum, right? So objects moving, like how much momentum does it have? We can multiply the two numbers. But most of the time when we solve physics problems, we're really looking at the object's change in momentum. And so it has momentum, some force is applied against it, and now the momentum has either increased or decreased. And so we're really looking at the change in momentum more than we are just the object's momentum. And so the change in momentum, right? So delta we know means change. And so if we have the change in momentum, your mass isn't going to change. So the only thing that can change is your velocity. And so we're looking at, right, if I do it in terms of M final minus initial, right? Because these are the things that can change. And a lot of times one of these guys, right, is going to be zero. You're starting from rest, this is zero. You're applying the brakes to your car, this is zero, right? You have a change in momentum of your car, that there's got to be a force, that an unbalancing force that makes that occur. So a lot of times in physics, it's not just the momentum that we're concerned with, but the object's change in momentum, right? And so what causes that change? Well, forces cause that change. So this is where this idea of the impulse momentum theorem comes into play, and why it's so closely related to stuff we've already learned, which I think makes this a little bit easier, because it comes from Newton's second law. And so when we do this, though, we drop off the sigma. And so what you've got to remember is that this, right, is representing all of the forces in the direction of the acceleration, right, the resultant force. And so what we do, I mean, you can leave it in there, you'll just not see that happen often. So we look at F equals ma, where F is the resultant force acting on the mass that causes the acceleration. But when we learned acceleration, we learned that acceleration was change in velocity over change in time, right? So I want to substitute in delta V over delta T. okay? Now, what is change in velocity? Change in velocity, as I showed you a minute ago, is your final velocity minus your initial velocity, right? Or if you're using VF minus VI, right? Any of those is fine. For again, just because AP, this is the way they would write it. That's kind of the way I write it. And you don't have to have delta T, but it's this idea of this force is being applied over a time interval. Our velocity is changing over a time interval. But if you didn't write delta T, that wouldn't be wrong. We would just assume that's what you're using the T for. But then what I want to do is I want to multiply both sides by delta T. Right? And so then I have this. Force times time equals mass times the change in velocity. Right? Again, change in velocity is delta V. Now we have this thing over here. We have force and time, right? And so I've been talking about the mass and the velocity and then force and time and how we can apply bigger forces for shorter times and vice versa. And so what happens is this idea of force and time is a new quantity. I don't know why they don't put it directly on your formula sheet. But it's what we call impulse. And so again, I don't know exactly why J. I should Google it and see if there's any logical reason, but I haven't seen it. But I've also seen, and this was when I was teaching IB, I've seen them use an italicized I. But in a textbook, you'll see J. J is what we call impulse. And then on the other side, right, we have, so this is kind of what we, from Newton's second law, this is what we get, right? This idea of force times time, that's impulse. Well, MV, right, MV represents the final momentum. And then MV naught represents the initial momentum. And so a lot of times one of these is going to be zero anyway, because we're always looking at starting objects or stopping objects. But again, this is really the change in momentum, right? From final to initial. And so this is what we call the impulse momentum theorem. This idea, this is the concept. The impulse equals the change in momentum, right? It's not impulse equals momentum, it equals the change in momentum because you're applying an unbalancing force over a period of time, it equals the change in momentum, right? And so we have these different things, and this is why I wish I got to make the formula sheet because I would make it a lot better than what they do. You have momentum, and I believe it's written just like this on your formula sheet. They don't give you this, and I guess I'm okay that they don't give you this. The change in momentum, right? That just means final minus initial. Then you have impulse equals force times the time interval that you're applying your force, right? And so I would assume this and this should be on the formula sheet. They give you this, but not directly. And then we have the theorem, which says the impulse applied to an object is equal to its change in momentum, right? So this is what I call the big idea. That's the big concept. So we have the big idea. This is the big idea. The impulse equals the change in momentum. But what I call the nuts and bolts equation, meaning, so in the conservation of momentum has the same idea. When we get into the energy unit, we kind of have the same idea there. Like we have big ideas, but then the big idea doesn't actually do the work of solving the problem. This is what I call the nuts and bolts equation, right? Substituting in what is impulse really equal to, what is the change in momentum really equal to? And so when you solve these problems, this is the guy that really gets it done. What I call the nuts and bolts equation, right? This is the people in the factory actually making the cars. And this is the CEO behind his desk just saying, this is a great idea, go do it. I'm not telling you how to do it, right? That's kind of how things go. Questions on that? So what you can see though, it all starts from Newton's second law. This all comes from Newton's second law and the definition of acceleration. But now we have a completely new way of thinking in terms of, we don't care about acceleration now. We don't, but we do care about the force and time, the mass and velocity, and how are they related. And so we have the impulse momentum theory. And what I did was, what I drew up there, you'll see here, because I can't save the annotations, but I kind of typed it up to go with what I did, right? And so anything that's a collision deals with this idea of impulse and momentum, and that's what an engineer does, right? Civil engineers really don't do this, but mechanical engineers, people that design, things like that for cars, they're looking at how do we minimize the amount of force for an object that's already moving with a certain amount of mass. You in your car driving to school, you can't change the mass of your car, right? You might not put your book bag in the car, and that changes the mass tiny, but not enough to mean anything. You can affect how fast you're driving, right? And so that's why we have speed limits with that idea in mind. Because when you get in a car accident, if you're going 55 miles an hour and the mass of your car is 2,000 pounds, that momentum at impact is a constant, right? And so the engineers have to make that assumption, like, this is a worst case scenario. You're going 55 miles per hour in a 2,000 pound car. How do we keep you safe? Well, we need the smallest amount of force possible to you. Well, how do we do that? Because we can't change the left-hand side of that equation of m times delta v. It's going to go from 55 to 0, right? We want the force to be small. We have to make the delta t as big as we possibly can. And that's where they came up with the idea of seatbelts in the 70s. Then the across your chest seatbelt, right, which was better than the lap belt, which was just across your lap, because that lap belt didn't keep your top part of your body from smacking the steering wheel. But then they made airbags, right? And that became a game changer in terms of, making that delta t as big as they possibly can, right? And I'm sure they're coming up with the next, invention for that. Besides the fact that the parts in the car that can absorb the impact are taking the cabin where we sit and making the force go away from, right, the energy of the impact and the force go away from the people. And so that's what we're looking at. So you want to take that same idea with your egg container, because once you build your container, the mass is a constant. If you drop it from the same height every time, the velocity when it hits technically is a constant, right? You drop it from a higher height, then it's going to have a higher final velocity, but the air resistance on it is going to be roughly the same while it's falling, right? It increases as it goes faster, but the only thing you can then affect is the right-hand side of the equation. You want your egg to get the smallest amount of force. You want your container to not hit the ground and bounce way out, because that would be a bigger force also. You got to make the impact time as big as possible so the force can be as small as possible, right? That's why you want to look for nice cushiony types of things that absorb the impact really well, right? And that's kind of the idea behind a lot of engineering throughout the decades, right? And so we're looking at the net change of momentum and how it's 0 for the entire system for all the things that are involved. Each particle can gain or lose momentum individually, but this takes us kind of to that conservation momentum idea, that the system can't gain or lose momentum, just transfers from one object to another object to make the net change equal to 0. And so here's my equation for impulse, now that we've talked about it, right? And so you see, this is the impulse momentum idea. Whether or not you put delta P or J first, it doesn't matter. But this should be on your formula sheet. But if I remember right, what they did put on your formula sheet is they put this, I think, we just looked at it and I've already forgot, right? I think that's what they have on there. They have this equation and they have this equation. Again, it doesn't make sense to me. Why not? Because this is J, this is the impulse. Why not give you this separate equation, right? I mean, how hard is that? It's not like they're telling you the answers to something and then giving you this, or sorry, giving you that, but they don't do that. I don't know why. So it's something you, hopefully just by talking about it and doing it like we've been, through the unit, that you'll remember that, make the connection. And so it's all about the change of momentum and the impulse. Now, how does force and time compensate? So I'm going to kind of skip through some of these. So when you look at the impulse, if we look at it literally, right, the unit for force is a newton. The unit for time is a second. Well, that is what the unit for impulse is. Now, you got to think about this. I've told you, or I've shown you, that impulse equals a change in momentum. Now, you don't have to put this little vector above the P. It's okay not to do that. But think about this. If these two things are equal, right, and this has units of a newton times a second. And if you remember, I said for change in momentum, it's kilogram meter per second. Well, if these two things are equal, then these two units have to be equal. And they are, right? But you've got to remember that a newton is a kilogram times a meter per second squared. And then we're multiplying that by the second. So it cancels off one of these, right? And what am I left with? A kilogram times a meter per second, which is the same thing as momentum. So there's two ways to write the same unit. Generally, if we're dealing with impulse, we use a newton times a second. If we're dealing with momentum, right, it's a kilogram meter per second. But you could use a newton second, and here you could use a kilogram meter per second, and I'm sure you will see that done in some problem. And so that can't be like the world ends and you're like, I don't know what to do, because that's not the unit for momentum. It is the unit for momentum, right? And so again, that's just one of the fun things about physics and units. Now, looking at graphs. Now, we've had these graphs before. This would be the graph that we would get from the activity, and we would try to get this from your egg drop. When collisions happen, they generally don't happen with a constant force. And so this is a very common shape for any kind of collision. You kick a soccer ball, you hit a baseball. If we had force sensors on your foot or on the bat, you would see this type of graph. Now, we generally, for what we're doing, because we're not calculus based and all that, we would generally make this a perfect triangle. Sorry, I did not draw a perfect triangle, because this definitely is not a perfect triangle, and you'd have to do like integration, those of you in calculus, right, to get the area of that, right? And that's something you would do in AP Physics C, those of you that are thinking of that, or college physics, you would definitely do that. But here you see, this is when the collision starts, this is when it ends. So imagine when the object's going, and when it first, like you're driving or you're not driving, but you see a car crash, the car just starts to hit the guardrail or the telephone pole, right? That's when the collision starts. But then what happens is, as it's going, now the force, right, as it comes to a stop, that's when it ends. The maximum force occurs halfway through the collision, as you can see from here, right? And so there's a point when the peak force applies and now it's on the back end, but it's not a consistent force. A constant force would look like this, right? If if it went up and then went straight across and went down, and you had a constant force, right? We could deal with that in our physics because our force is constant. Constant forces make constant accelerations, and we like those. We don't like curves. But that's generally what happens when you use force sensors. The activity that we would normally do is you bump the cars into these force sensors and you get that graph using the LabQuest, you see that. But what it turns out is the area underneath this, right? So again, remember we can do slope or we can do area, right? And if I did the slope, well, that's force over time. That is nothing. That doesn't give us anything. But the area, right, is force times time. And from what we've already said today, we know that is equal to the impulse. And so if it equals the impulse, though, well, then we know it's equal to the change in momentum also. And so again, for us, there's going to be triangles or it's going to be squares or rectangles. Those are the only things that we can deal with. This would imply not a constant force, right, if it's a triangle. But if it's a rectangle or square, then it's a constant force. And so this area would obviously be 1/2 the base times the height for a non-constant force. If it looked like this, right, this would obviously be base times height. But the area is going to give us the impulse, which gives us the change in momentum. Then knowing the mass, we could solve for the change in velocity from our graph. So I did a baseball one because it's springtime. March is usually baseball, right? I'm sure Aaron's getting ready for some baseball here soon. And so you've got this 3 Newton baseball. So notice I made this italicized in a different color because I wanted you to notice the unit is not given in kilograms, but it's given in weight. It's moving at 30 meters per second. It's struck with a bat that makes it go faster. Now, right, if you throw a ball at a wall and it comes back to you, there's no way for it to go faster after hitting the wall and coming back because the wall would then have to give it, right, think in terms of energy, would have to give it energy. But because the bat is being swung, right, it's possible that it happens that it's going to go faster when Aaron throws the ball. If I was to hit it, it's probably going to go faster when it leaves my bat than it was coming towards that, regardless of how fast the pitcher is. And so again, there's that change in direction. So you got to remember that one of the velocities has to be positive, one has to be negative. And then notice the times, right? So you're going to see MS used a lot for the unit, and that's milliseconds. And we don't like milliseconds, right? So it wants us to calculate the impulse and the force. So again, you're going to see that, a lot of similarities to what we did, but we have the weight of the baseball, right? Or the force of gravity of the baseball is 3 newtons. So the first thing you should think about is, well, I don't want that. I want the mass. I'm going to take the weight and divide it by G. So 3 newtons divided by 10 to get 0.3 kilograms. Right? And I don't need to make this negative because I'm just using the equation to get the mass. We know mass doesn't have direction, right? That would be negative, that would be negative. The negatives would go away anyway. Now, again, depending on how you do this, if you went with the picture, the ball initially had a negative velocity because it's going to the left. And then when it hits and rebounds, it's going to the right with a positive velocity. It doesn't matter which is which. But one of these has to be negative. Calculate the impulse and the average force, and then our impact time is 40 milliseconds. We don't like that, right? It's like millimeters to meters. We want to convert it to this. I would say convert it right away so you don't forget. So calculate the impulse and the average force. So if you say, okay, well, impulse is equal to force times time, do we know the force? We don't, right? So I can't use this, but can I calculate the change in momentum? I can, because the change in momentum is equal to mass times change in velocity. And we know now that that is equal to impulse. So I'm really using this as my equation, right? Because we know that impulse, the big idea is the impulse is equal to the change in momentum. I can use J equals M delta V, or I could use delta P equals F times delta T, right? Because that's how we calculate change in momentum, and that's how we calculate impulse. So which version you want to use is really going to be dictated by what's given in the problem. So in this case, since we know the mass, and we now know that, right, the change in velocity, so final 42 minus a negative 30. So my difference here has to be 72 and not 12. That's where, if you're going to make a mistake, chances are that's because that's where you guys made mistakes when we calculated the acceleration of the baseball. We probably had this picture done already where we didn't care about the mass of the force. I just said calculate the acceleration of the baseball. But now we care about those other things. But we need to be able to still get the change in velocity, right? So that change in velocity is 72. You multiply that by 0.3, and you get 21.6 kilogram meters per second, right? Or Newton seconds, because we know they're the same unit. So this is what we would do for the first part to calculate the impulse. But then it says calculate the force. We would say, well, impulse is equal to F times T. So the force, right, the unbalancing force of the bat hitting the ball is going to equal the impulse divided by the change in time. So we've calculated the impulse, and we simply are dividing this by 0.04 seconds to get 540 newtons. So could we have done this a completely different way with nothing that I've shown you today? We could, right? Because, well, we could calculate the force anyway, because we know that force equals mass times acceleration, and acceleration equals change in velocity and change in time. So what we're doing is we're getting rid of having to use this combination and just looking at the big idea of impulse equals change in momentum, and force times time, which is impulse, equals mass times change in velocity. So it's really just a different way to look at the same problems that we've already done in the past. And anyway, so again, and tomorrow we're not learning anything new. We're just going to reinforce some of these and then play with the crash test dummy simulation. So you got a 2 kilogram object, okay? And so this is using some kind of force sensor here. We graph force first time. So how is this? This tells you that it's a constant force, right? Not a big constant force of 2 newtons for 0.5 seconds. It's moving to the right with an initial speed of 1 meter per second when it experiences the force shown here. What is the object speed and direction after the force ends? So this is what we're given, right? We know those two numbers from the graph. We can see that the 2 Newton force is applied for 0.5 seconds. Excuse me. There's allergies today. Nobody's here today, so all's good. So what we can calculate, first I would calculate the initial momentum of this object, right? Really easy math, 2 times 1. Then I would calculate the impulse. Since we know that the area of this graph for a constant force is simply going to be force times time. So 2 newtons times 0.5 seconds, right, is 1 Newton seconds. And we know that the change in momentum is equal to impulse. And so the final momentum minus the initial momentum is equal to impulse. Again, you can put an F here if you want to. If you don't, it just assumes it's the final. And so the final momentum is going to equal the impulse plus, or the impulse, or the initial momentum plus the impulse, right? Which means 2 kilogram meters per second plus 1 Newton seconds. And again, remember that a Newton second and a kilogram meter per second are the same unit. So my final momentum is 3 kilogram meters per second. This is a positive force, so we can assume that if the object was moving in this direction, the force was also in this direction. And so it made my final momentum bigger, right, than it initially was. And so now that I know my final momentum, I can set that equal to mv and take the momentum and divide it by the mass, which was 2 kilograms, to get 1.5 meters per second. And so because this is positive, well, I know that the final velocity is still to the right, right? If I was saying this was moving to the right, this positive force, so that's like something's moving and you hit it while it's moving, now all of a sudden it goes faster, right? So you hit it briefly, or your friend's on a skateboard and they're going by you and you give them a push to make them go a little bit faster, right? You've applied an impulse that has increased their momentum, right? And so after you've pushed them, applied that force for that time, they have a greater momentum because of it.